Welcome to our second lecture on compiler construction. In today's lecture, we'll take a look at the structure of typical compilers and also in the second part of this lecture take a look at the first part of a compiler, the so-called lexical analysis. So today we'll start with an overview to define a compiler, what is a compiler, and what are the typical tasks of a compiler. We'll take a look at the structure and stages of a typical compiler. And in the second part of today's lecture, we'll talk about deterministic finite automata and how to use them for the first part of our compiler, to use them for lexical analysis or scanning. So compilers are everywhere. The original idea behind compilers was to enable humans to be able to program computers in higher levels of abstractions. So you don't have to really know what the machine is doing, you have to be able to formulate your problem on some higher level of abstraction like mathematical formulas, and very early approaches to this were already invented in the 1940s with Konrad Zuse's Plankalkül, which was a theoretical experiment because he didn't have any hardware available to implement it. The first version of Plankalkül was actually only implemented in the 1990s. But there were other early programming languages for primitive early computers like Fortran, Lisp, and a language called A0, and those were already invented in the 1950s. Now today the situation has changed quite a bit. So you have very many different source languages, you have very many different target platforms. So as you see on the right hand side, there's just a short list, an excerpt of the number of languages that are available and are in use today to, create software for computers. But compilers are not only used to translate high-level abstractions into whatever your machine is going to understand, so your binary code, but as we've seen in the first lecture of this course, there are also additional uses of compilers. So you can do static analysis, so you can figure out and prove properties of a program. You can check for correctness of a program given certain constraints or definitions, which is verification. You can also use compilers to do hardware synthesis, so you have a high-level description of hardware instead of software, and you can create a chip out of this. You can also do source-to-source transformations, for example, to optimize code, and you can do just-in-time compilation to enable independence from a certain machine instruction set, and just doing this translation, the final step, at runtime on the machine you're executing the code on. So what does a compiler do? A simple definition of a compiler is a tool that translates software that's written in one language into another language. And to do this, a compiler must understand both the form, we call it syntax, and the content or meaning, so we call this semantics, of the so-called input language. So the language we want to use to write our programs in, the language the compiler is going to understand and translate later on. In addition, our compiler needs to understand the given rules that govern the syntax and the meaning in the output language. So to translate the meaning of a program from a source language to an output language, which might be machine language, we need to know how to translate this meaning, because obviously when we compile code, we are not supposed to change the meaning of our program. And after all, for doing this, we need a scheme for mapping content from our source language to our target language. The two requirements a compiler must fulfill in any case is it must preserve the meaning of the program being compiled, and it should be able to improve the input program in some discernible way. So we've already seen this diagram of the compilation process black box before. So our compiler is just symbolized by this question mark or big black box we're going to explore during this semester. And the task of our compiler is to take this input source code, like this piece of C source code, and to generate some sort of, for example, binary machine code out of it. So how does this work? We've already seen this compilation process in detail, but it's a good introduction for the following steps. So our compilation process, of course, should generate code that should be executed on a computer. And we want to execute something translated from a source code in our high-level language, for example, written in C. And we've already seen for C code, we have this preprocessor, which does very primitive text replacement and generates C source code again, this time preprocessed, so all the preprocessor statements beginning with hash marks are replaced by just simple C code. So it's simple text replacement, and we've seen the problems that might occur with this in the previous lecture. This code is then passed to our compiler. The compiler does all sorts of transformations and usually generates assembler code as an output. So this assembler code is still human readable, but it's already on a level that is very close to what our machine is able to understand. Now, this is still human readable, so we have to transform this into some sort of machine code, binary code that our computer can understand. So to do this, we use a tool that's confusingly also called an assembler. And this assembler then takes this assembler source code as an input, so the human readable code, and generates binary code that's understandable by our computer. So this is called machine code or object code. And usually our programs are more complex, so they consist of more than one source code file. So we have to tie them all up together into a final program. This is the task of a linker, so it takes a number of machine code object files, a number of .o files, puts them all together, and for all functionality that's not included in the object files, it can also add a number of libraries which are provided by the system or by yourself as a programmer. And out of all of this, it generates an executable program, an ELF file, for example, on Unix systems, which then can be put on your disk, can be uploaded to the network, whatever you want to do with it. And when you want to run your program, your operating system loads the executable file from disk, for example. This is the task of a loader. It might load additional system components like shared libraries. We're not going to discuss these in detail here. And then it copies all this executable code from disk into your main memory of your computer. And then finally, you can run your program. Of course, when you develop programs, errors might show up, and it's very good to have an ability to look at errors at runtime. So at runtime, you usually have the ability to use a debugger to stop a program, to look at internal state of a program, so at the values of a variable or where your program is actually executing right now, in which function, in which line of source code was my program when a problem showed up. So this is the task of a debugger. So to take a closer look at the structure of a compiler, we use this simple diagram here. So we have our source code on the left-hand side and our binary target program on the right-hand side, and our blue box here just is our compiler. And this compiler, in the most simple case, consists of two parts. The first part is called the front end. So the front end takes place of understanding the form or syntax and the content or meaning, semantics of the input language. Then we need a scheme for mapping the content from the source language to the target language, symbolized by the arrow here. And then in the backend, this is responsible for understanding the rules that govern the syntax and the meaning of the output language. So essentially we split the task of our compiler into two big parts. The front end, responsible for syntactic and semantic analysis, and the backend, responsible for transforming whatever we found out about the program we are going to compile into code that does the same thing on your machine. Now, there's one additional thing that's really important, and that was one of the requirements we asked of a compiler in 2 slides ago. So we want to be able to improve the input program in some discernible way. And this is the task of an optimizer. An optimizer is usually a part of a compiler that's between the front end and the back end. And this optimizer should be as general as possible in any case. So this optimizer should not really depend on properties of your source code or your input language. And in many cases, it also is independent from properties of your target machine architecture or machine language. So we need some sort of common language to interface the front end to the back end, or the front end to the optimizer, and the optimizer to the back end. Now, if we only have a structure consisting of a front end and a back end, we can use something called an intermediate representation, or IR, to connect both parts. And the idea is now, if we put this optimizer in between the front and the back end, we can still use this intermediate representation to perform all optimization operations on. So this intermediate representation is an important form, and we'll take closer looks at what intermediate representations look like later on. So it's important to enable you to write compilers that are easy to maintain and easy to change when you want to do changes to your input language, or maybe you want to retarget your compiler to a different machine architecture. So let's say from x86 to an ARM processor. This intermediate representation has a number of additional advantages. So very early compilers directly generated machine code. So they more or less scanned and parsed your code, and during the process of parsing, they already generated code in the output language. Now this caused a lot of problems as shown in the picture here. So let's say you have a number of input languages like Java and Pascal and C and C++, and you have a number of machine architectures like Spark and MIPS and PowerPC and Intel and so on. If you want to write compilers in this early way, you have to write a combination of front and back end for, yes, all of the combination of source and target language you want to support. So essentially, if you want to have a Java compiler that's available for all your architectures on the right hand side, you would have to write 4 different compilers. And if you want to write a Pascal compiler, you have to write 5 completely different compilers. Now, the thing is that the first part of the compiler, our front end, is identical for all our 5 Pascal compilers, whereas the back end is identical for all of the 5 languages targeting, for example, Intel processors. So essentially what we want to achieve is we want to be able to have this intermediate representation as sort of a common ground to connect the front end and the back end. And this helps us to reduce the number of compilers we have to write. So we separate the front end from the back end. We have the front end for all of our languages here, Java, Pascal, C, and so on. Always generate the one and only same intermediate representation. And that's all our front end is concerned with. So it does scanning and parsing and generates not machine language, but only an intermediate representation. And the back end of a compiler can then take care of transforming our intermediate representation into whatever machine language you want. So you can have a backend for Spark, which can compile intermediate representations generated by all of your source code languages on the left-hand side. And this has a number of advantages. In the original approach on the left-hand side, if you had n source languages and m targets, you would need n times m compilers to support all of the languages and all of your target platforms. And if you use an intermediate representation that's common to all of your backends and all of your front ends, you only need to write n front ends, all generating intermediate representation, and m backends, all taking intermediate representation and generating machine language. So you only need n plus m compilers now, which makes life quite a bit easier. But intermediate representations have additional advantages. It's very easy to change the source or target language just because you only have to change half of your compiler and not all of the parts in the front and the back end. Optimizations are made easier because they need to be developed only for the intermediate representation and not on a level of source code or on a level of machine language. And this intermediate representation, if you don't have a backend so far, can even be interpreted directly. So you can write a program that actually is able to read your intermediate representation and execute it as a program to test your front ends. Now, if we dig deeper into the stages of a compiler, this is what it looks like. So we've already seen our front end consists of lexical analysis, and then we have the syntax analysis. We have an additional step called the semantic analysis, which checks if all of the stuff we put in there makes sense. So we, for example, don't try to assign a character string to an integer variable. After that, we have code optimization, and then we have code generation. So let's look at the first step here, the lexical analysis. So the lexical analysis takes your program source code, which is just a stream of characters. So it reads one character after the other. And the task of our lexical analysis is to split our source code into so-called tokens. So you can compare this to trying to read a book. So you start to figure out what are the words, what are maybe the limits of sentences by figuring out where's a comma or a full stop. So essentially you only try to split this just mess of characters, that's the input, into something that has some annotations, like the first 5 characters of my input text are a word, and that word has the text, for example, house. So these things are called tokens. Tokens can be recognized using regular expressions. Regular expressions can be implemented using automata, and the second part of today's lecture will take a closer look at how this works. So tokens are character sequences that are relevant in some source language grammar. So our example on the bottom here has a character stream which contains the characters x equals y plus 4 and 2. So it's just ASCII characters, just as we've seen before, a stream of ASCII encoded characters, which can also be seen just as a stream of numbers. So this character stream now is split into something. So we start finding an x, and in our language we want to compile, we say x is a variable name. So x identifies a variable, so we say we found something that's called x, and we annotate this x with the information that it's an identifier. So it's a name of, for example, a variable or something else like a function. The next character we encounter is an equals sign. So an equals sign has special meaning in our language. An equals sign might be an assignment operator. So we say, okay, the next thing we found is this equals sign, and we annotate it with the information, oh, it's an operator. Okay. Then we continue. We find another ASCII letter here, a y. So y again is an identifier, so we output the information. Okay, next thing that's coming up is a y. This is an identifier again. Then we find the plus sign. Plus again is an operator. And then we find something that consists of more than one character. So we find the character 4, and we figure out that after that character 4 there's another digit coming. So it's a 2. And we can make the task of our compiler easier if we can already get some sort of a meaning to this. So we say, okay, if we find sequences of digits like a 4 and a 2, we can say, okay, this sequence of digits 4 and 2 is actually a number, for example, an integer number. So what our lexical analysis does, it takes this character stream as an input, and it generates these tokens in sequence as an output. So it reads from front to back, and it starts when it reads the x, it outputs, oh, there's an x, it's an ID. Then it reads the equals sign, oh, it's an equals sign, it's an operator, and so on. And finally, it reads 42, or the characters 4 and 2, and it says, oh, these characters 4 and 2, they make up a number. So this is the output of a lexical analysis. So we just split up our character stream into identifiable tokens and give them some sort of relatively primitive meaning according to a very simple mechanism. So the next part of our compiler is the so-called syntax analysis. Syntax analysis takes the output of our lexical analysis, so our token sequence here, and generates something that tries to reconstruct the structure of our program. Now, as you've seen in programming so far, very many programming languages have sorts of structures. So a structure might consist of, you have several functions on the top level. Inside of these functions you can have blocks or loops or if conditions and so on. So the idea is the structure we see automatically as a human because we wrote it and we used indentation and brackets and stuff like that to make this clear in our source code, to make this information available to our compiler. So the syntax analysis takes some sort of structure definition of the source language. The structure definition is called a grammar. So it just describes how well its structures actually look in our programming language, like a grammar for a natural language that describes what the correct order, for example, of words in a sentence is. So, for example, you have a subject first and then a verb and not the other way around, because that would be an invalid sentence that nobody would be able to understand. So the syntax analysis tries to reconstruct this structure here as a tree from the tokens we get. So the parts of our trees are just our tokens that were output by the lexical analysis. And in order to construct this, it consults this grammar, and this grammar is written as a set of rules. For example, we have a set of rules here that starts, okay, we have a grammar for an expression, so an arithmetical expression, and that might consist of a term and optionally some other part, which is a plus or minus, and another term. So you see we have so-called terminal symbols, which are already identifiable as a token, for example our plus sign here, and we have so-called non-terminal symbols like expression or term, which have to be resolved to something else in our grammar because they stand for classes of objects here in our grammar. So if we resolve our expression to term plus minus term, we need to define term now. So that's why all these are printed in bold, to make it easier for you to differentiate between terminal and non-terminal symbols. So a term can be a factor, then optionally an operator, which is a multiplication or a division sign, and another factor. Now we need to resolve factor, and factor again can be a bracket containing an expression and a closing bracket, or an identifier. So here's our identifiers, or it can even be a number. So when you take a closer look at our grammar, we start with an expression. That's a term plus minus term. Well, so our right hand side here, and then this term has only simple factors here, and one of the factors is the identifier y, and the other of these factors is the number 42. Note that we haven't given any definition of the grammar part for our assignment with the equals sign, so this grammar on the left hand side here only fits for the lower right half of our tree. So our syntax analysis recreates the structure of our program and represents it in a form that's understandable by the following stages of a compiler that need to make sense out of this structure. So let's go to the next stage of our compiler, which is the semantic analysis. So the semantic analysis takes our syntax tree as an input and finally outputs our intermediate representation. So the semantic analysis first does a name analysis. So it checks the definition and scopes of symbols. For example, if we use a variable x, has this variable been declared before? Are there any conflicts between names of variables and functions? Are there any conflicts, for example, between names of variables and reserved keywords? It also does a type analysis. Type analysis is concerned with whatever the contents, for example, of a variable is. So are we actually trying to assign a string to an integer variable, which would be an invalid operation, which we would not be able to represent on a machine level, so we would just generate an error and tell our programmer, oh, something's wrong here. And the final task of the semantic analysis is to create so-called symbol tables. We've seen symbol tables before in the C introduction. So symbol tables take all of your identifiers like variable names and function names, and they map them to their respective types, so to integers or characters or functions, and they indicate where to find them in your source code. So when we have the semantic analysis, we have generated this magic intermediate representation, and now the first part of a compiler is actually finished. Then we can use code optimization as the next step. Code optimization is completely optional. You could directly generate code from the semantic analysis, but obviously it's better to invest more work at compile time to optimize code than just accepting that all of the program runs you're doing with your compiled program later take longer because you didn't spend another 30 seconds on optimizing your code during compilation. So optimization is optional, but it's an important step so you can actually make use of all the performance your expensive modern computer has. So code optimization analyzes the intermediate representation that was parsed by semantic analysis here. It tries to find redundancies. For example, if you initialize a variable x equals 1 and in the next line you directly write x equals 2. Now obviously the first value of x is never used anywhere, so our compiler can figure out, oh yeah, this is part of my intermediate representation, but it doesn't make any sense because the first assigned value to x is never used, so you can throw it away. And there are quite a number of different optimizations you can apply, and this will be an important part in the second half of this course. Very often, different stages or levels of optimizations can be applied to different intermediate representations. So in real-world compilers, sometimes you not only have one intermediate representation, but a family of intermediate representations that are somehow related to enable easier optimizations. But for the sake of simplicity, just let's assume that there's one and only intermediate representation that is used. So code optimization is actually a container for very many different optimization steps that can be executed in some order. And the important thing here for our compiler is that code optimization always operates on intermediate representation as an input and always generates the same intermediate representation style as an output. Obviously, what we want is that the intermediate representation that is output is more efficient, so it can, for example, execute faster than what is input here as the result of the semantic analysis. And our final part of our compiler is then code generation. So we have our intermediate representation, and as the name says, this is on a higher level than our machine code. It's somewhere in between the source code and the machine code level. For example, it has very primitive instructions, but it might still have something like variable names, whereas our machine doesn't know anything about variables, so you have to replace variable names by memory addresses the variables are stored in, or register names your variable currently is copied into in order to generate your machine code that's executable. So code generation determines and outputs equivalent machine instructions for all of the components of your intermediate representation. This part is called instruction selection. So which machine instructions can be used to implement a certain operation on intermediate representation level. It determines the correct instruction order with respect to constraints of your processor. So if you've taken a class in computer architecture before, you know there's pipelining, and certain operations in pipelines have to be delayed because the value that they use is not ready because it's still used in a previous pipeline stage or generated in a previous pipeline stage. So our backend has to know all of this to generate correct code, and there you can also do additional optimizations to exploit instruction level parallelism, so you can do instruction scheduling in order to avoid latencies or stalling your processor as much as possible. And your code generation also assigns, as we've already seen, variables to registers and memory locations, so our machine that doesn't know anything about variables can actually operate on the data inside of your program. And the final thing coming out of code generation is then a binary program, your machine code. So this is an overview of the stages of a compiler, and in the second part of today's lecture, we'll take a closer look at how the first part of our compiler, the lexical analysis, actually works.